esas konuşmacımız İngilizce. 9.30'da başlayacak dediğimiz ama test edebilirsiniz.
Şu an giriyor yayına.
Tamam.
Ne oldu?
Nerede görüyor?
Ses. Ha, burada gözüküyor ses. Tamam, sen git. Şimdi gelmiş.
Sen görebiliyor musun?
Ben ses geliyor şu an. Şu mu? Çok iyi. Neymiş bu dediğin yapmaya bakın. Nereden göreceğim?
Şöyle küçük aşağı.
Şuradan.
Onun bir diğer sayfası yok mu? Şuradan gir bakayım.
Bize klavye ne ya? Neyse, nerede yapacağım? Ne yapacağız?
Mücahit'le ilgili.
Bizim kendi grubumuzda
Tamam, şu işte.
Benimki lazım. Girsene orada. Allah'a çalışıyor. O değişti bak. Şu aşağıya bir baksana.
Şu işte abi. Renk. Değil mi? Evet.
Bunu nasıl gönderiyoruz?
Bu ne yapayım bana? Şu değil mi?
Tamam. Yani aslında oradan kesilse. Yayına gidiyor. Evet, konuş.
Test, senin değişikliği. Test 1, 2, 3, 4, 5, 6. Senin değil, test pro.
Buraya geliyor mu? Geliyor mu? Konuş.
Senin değil, test pro. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Senin değil.
Tamam mı?
Ses geliyor mu?
Şu an çalışıyor. Kapalı mı? Ha, ses kapalı.
Senin değil, test pro. 1, 2, 3.
Tamam. Buyur. Bunun kamerasından geliyor sanki.
Elektriği. Bakarız şunu da. Buraya versene sesi. Buraya versene sesi. Şöyle çıkalım.
Böyle yapabiliriz.
Aynen.
Sen burada. Tamam. Getireceğim. Ben sana bakar.
Ülkemizde bu alandaki geniş spektrumda araştırmacıları bir araya getirerek hem paylaşma hem de öğrenme olanakları sunuyor.
Bakayım.
12 yıldır ilginin bu kadar canlı kalmasının en önemli sebeplerinden bir tanesi de budur. Ulusal Yazılım Mühendisliği Sempozyumu temel alanla birlikte yazılım test mühendisliği, sağlık için yazılım mühendisliği, yazılım modelleme ve lisansüstü testler tematik alanlarında bildiriler kabul edilmiştir. Bu yıl temel alanda artmış, sağlık için yazılım mühendisliği alanında 6, yazılım modelleme alanında 6, yazılım test mühendisliği alanında 16 ve lisansüstü çalışmalarında 8 olmak üzere toplam 96 bildiri sunulmuştur. Bunlardan 75 adedi kabul edilmiştir. Bildiriler en az 3 hakem tarafından titizlikle değerlendirilmiştir ve bu değerli çalışmalarından dolayı hakemlerimize teşekkür ederiz. Sunumları takiben bu bildiriler CEU sitesinde çevrimiçi olarak yayınlanacaktır. Bu yılki davetli konuşmacımız University of South Wales, Avustralya'dan Bilgisayar Bilimleri ve Mühendisliği bölümünden Doçent Doktor Salil Ane'dir. Ve konuşmasında blok zinciri teknolojisi ve bu teknolojinin mevcut sorunlar için getirdiği çözümleri belirleyecektir. Kendisine bunca yolu aşarak bizimle beraber olduğu ve değerli görüşlerini bizlerle paylaşacağı için şimdiden teşekkür etmek isteriz. Sempozyumda bir de panelimiz var. Bu panelin konusu büyük veri ve yazılım mühendisliği. Panelde birbirinden değerli konuşmacılarımız olacak. Panel konuşmacılarımız Profesör Doktor Fevzi Belli, Profesör Doktor Semih Bilgen ve Siemens firmasından Sayın Volkan Şimşek olacaktır. Tüm konuşmacılara şimdiden katkıları ve paylaşımları için teşekkür ederiz. Çalışmalarımız sempozyumdaki çeşitli oturumlarda paylaşan tüm konuşmacılara da ayrıca teşekkürlerimizi sunmak isteriz. Bu çabaları gelecek yıllarda yazılım mühendisliği alanında daha başarılı çalışmalara yol açacağına olan inancımızı tekrarlamak isteriz. Sempozyumun gerçekleşmesini mümkün kılan Sabancı Üniversitesi'ne ve etkinliğin gerçekleştiğimiz boyunca çeşitli görevleri yerine getiren yönlendirme, program ve düzenleme komitelerinin üyelerine, tematik alan başkanlarına, web yöneticileri ile yayınlama, tanıtım ve mali işler sorumlularına da ayrıca teşekkür etmek isteriz. Sponsorlarımız Siemens, Havelsan, Türk Büyük Teknolojileri, ARGE Merkezi ve Eğitimciler verdikleri destekler için şükranlarımızı sunuyoruz. Hepinize başarılı ve verimli bir sempozyum dileklerimizi sunuyoruz. Teşekkür ederiz.
Merhabalar. Şu sunum hazırladığımdan çok küçük organizasyonla ilgili birkaç detaydan bahsedeceğim. Öncelikle organizasyon komitesi adına 12. Ulusal Yazılım Mühendisliği Sempozyumu'na hoş geldiniz. Bu sempozyum, bu seneki UYMS sempozyumu organizasyon kısmı Sabancı Üniversitesi'nden ben Cemal Yılmaz ve Hüsnü Yenigül Hocam üstlendik. Program komitesinde Hacettepe Üniversitesi'nden Ayça Tarhan Hocam ve ilk eden İzmir Yüksek Teknoloji Üniversitesi'nden Murat Akın Hocam vardı. Hepsine, kendilerine çok teşekkür ediyorum. Onlarla çalışması büyük bir zevkti. Bir teşekkür de tabii Hüsnü Hocam geliyor. Ona da çok teşekkür ediyorum. Ayrıca Sabancı Üniversitesi'nden o kadar çok insanı mobilize ve dahil terörize ettik ki saymaklarıyla dolayısıyla Sabancı Üniversitesi'ne ekstra teşekkür etmek istiyorum. Satın almadan Sant'taki ve mahalle işletmeler hepsine çok teşekkür ediyorum. Hep duyardım. Tabii ki sponsorlarımız, başta ana sponsorumuz Siemens olmak üzere sponsorlarımız Airties, Avelsan ve Kuyutuk'a çok teşekkür ediyorum. Onlar olmadan böyle bir organizasyonu yapmak mümkünatı yoktu. Gerçekten çok teşekkürler kendilerine. Hep duyardım ne anlama geldiğini çok anlamazdım ama gerçekten bir mesleği organize etmek gerçekten meşakkatli ama bir o kadar da keyifli bir iş. Burada bir görüntüler var verebilirsem. Görmüyorsunuz ama çocukla çalışmak zorunda kaldım. O da benim büyük oğlum futbol antrenmanından sonra bize yardım ederken. En iyi lisansüstü öğrencilerimize balyoz verdik. Gereken gördüğünüz mavi kameraları çekmek için kullanıldı. Neyse ki süreçte hiç kimse zarar görmedi. Şimdi katılımcı, bu slaytlı bir sorun olmadığı için kusura bakmayın. Katılımcı çantası hazırladık. Özel bir tasarladığımız, heyecanla sipariş verdiğimiz bir çanta vardı. Fakat ürettik bir facia olunca çantayı size verdi ve kararını aldık. Belki olmaz program komitesi üyelerimizle de konuşup belki de hatırladınız yarın ya da bugün. Onun yerine elimizde geçip çıktı. Dosyalar aldınız. Bu önemli bir özetleri kitabını bulacaksınız. Dosyada programı bulacaksınız. Program çok işleyeceğiz. Önemli bilgiler dokumenını bulacaksınız ki orada özellikle galeriyle ilgili, geziyle ilgili detaylı bilgiler olacak. Sponsor broşürlerimiz var, not defteri ve kalemlerin içinde. İnternet iki şekilde bağlanabilirsiniz. Ethereum hesabınız varsa Ethereum'u kullanabilirsiniz ya da Sucast wireless connection'ı kullanabilirsiniz. Detaylar yine buradaki önemli bilgiler dokümanından. Öğrenimleri üniversite merkezinde verilecek, üniversite merkezi tam o çimenlik alanı ortadan bakan bina. Çıkınca zaten hep beraber gideceğimiz için sorun olmayacaktır. 1+3 olarak var burada. Bir ana yemek, en fazla bir ana yemek, en fazla 3 yan yemekler. Yaka kartınızı göstermeniz yeterli bunun için, öğle yemeğini almak için. Öğle yemeği sadece pazartesi ve salı günü olacak çünkü officially çarşamba günü sempozyum sonlanıyor. Galeri yarın Adil Balıklı olacak. Adil Balıklı'da sahilde geniş 17'de o park ettiğimiz B3 otoparkında o sunum teknolojide bölümlük otoparktan kalkacak. Geniş ise 22'de Adil Balık'ta fasıl olacak. Yaka kartlarınızın arkasında 2 tane bilet görmeniz lazım. Biri yemek bileti, biri içecek bileti. Bunları getirmeniz gerekiyor. Orada toparlayacağız. Ve sizden rica ediyorum, içecek biletinde içeceğiniz şeyi işaretledikten sonra, işaretledikten sonra garsona verirseniz çok sevinirim. Çünkü ona göre ödemleri yapacağız. Yani burada işaretlenmesi önemli. Adil güzel bir balık görüntü, balık lokantası Tuzla sahilde, denize nazır. Tavsiye ederim gelmenizi. Bu da Fener Balat gezisi, bu da güzel bir gezi olmaya aday. Ahmet Faik Özgür'le ve Egemen Demircioğlu ile gezeceğiz. Sanırım Ahmet Faik Özgür'le yanlış hatırlamıyorsam bu konuda zaten kitapları olan biletten. Gidiş 14'te çarşamba günü, bu son gün panelden sonra 14'te P3 otoparkından kalkacağız. Yaklaşık bir buluşmamız, eğer Beyoğlu'ya gitmek isterseniz Fener Rock Reklamesi önünde saat 15.30'da olacak. Gezilecek yerlerin listesi, bu 3 saatlik bir yürüyüş, gezilecek yerlerin listesini önemli bilgilerle bulundurabilirsiniz. Geliş ise bizden ayrılırsanız sonra da devam etmek isterseniz Balat otobüs durağından 18.45'te olacak. Çok hızlıca geliyor. Bir anketimiz var. Ankete ulaşmak, doldurmak için UYMS.org adresinden en sonunda anketi göreceksiniz. Canlı yayınımız var. Sanırım ilk defa canlı yayın yapıyoruz. Umarım çalışıyor, kontrol edelim. Canlı yayınımıza da eğer arkadaşlarınıza haber vermek isterseniz canlı yayın linkimiz var, bağlantımız var web sitesinden. Keyifli bir UYMS diliyorum. Hepiniz tekrardan hoş geldiniz. Şimdi öpüyorum fazla uzatmadan sözü Mühendislik ve Doğa Bilimleri Fakültesi Dekan Yardımcımız Selim Balcısoy'a veriyorum.
Sabancı Üniversitesi olarak. Ondan sonra bir sürü arkadaşımız yemin etmişti bir daha konferans düzenlemeyeceğiz diye. Ama o zaman Sabancı Üniversitesi'nin etrafında otel, yemek yerleri bu kadar yoktu. Otel yoktu zaten. Şehirde düzenlemek durumunda kalmıştık. Şimdi artık burada düzenlemek bizim için büyük bir keyif. Sizlere Sabancı Üniversitesi'ne hoş geldiniz diyorum. Çok da fazla lafı uzatmak istemiyorum. Ama bir iki noktaya değinmek istiyorum. 2006'dan sonra biz farklı hocalarımız, farklı uluslararası konferanslara da destek verdi. Ama ulusal konferanslara destek vermeye devam edeceğiz. Bu bizim için çok önemli bir şey. Çünkü CS konusunda ilgi artıyor. CS konusunda araştırmaların da aynı düzeyde artmasını istiyoruz. İlginin arttığını biliyorsunuz, burası bölümsüz, programsız bir okul. Öğrenciler seçebiliyorlar. Son senelerde CS seçen öğrenci sayısında inanılmaz bir artış var. Bu çok önemli bir şey. Bunun araştırmaya da etkisi olacağını düşünüyoruz ulusal bazda. Bir de sponsorlara ayrıca çok teşekkür etmek istiyorum. Yine 2006 ve daha sonra yaptığımız ulusal veya uluslararası konferanslarda Türkiye'de sponsor bulmak bu tip konferanslar çok zordu. Şimdi 4 tane sponsorumuz var. Bunun kıymetini bilelim. Ben sözü burada Hüsnü Hoca'ya veriyorum. Ve çok teşekkürler. Hoş geldiniz. Kampüsün tadını çıkartın bu arada. Çok güzel bir kampüsümüz var. İyi günler diliyorum. İyi çalışmalar.
Evet, ben de herkese hepinize hoş geldiniz demek istiyorum. Aslında biraz geç başladık ama herhalde aktarmak istediğimiz tüm bilgileri aktardık hızlı bir şekilde. Ve aslında davetli konuşmacı oturumuna geçebiliriz. Bence ekleyeceğimiz başka bir şey yoksa. Oturum başkanımız Murat Hocamız. Murat Hocam, size davet edeyim.
Tekrar merhaba. Bugünkü sempozyumumuzun davetli konuşmacısı Salil Kanhere ve kendisinin kısa bir özgeçmişini sizlerle paylaşmak istiyorum. Doktor Salil Kanhere MS ve PhD derecelerini Drexel Üniversitesi'nden aldı ve halen University of South Wales Avustralya Sydney'de doçent olarak görev yapmakta. Aynı zamanda Data 61 CSIRO'da da bir araştırmacı olarak görev yapıyor. Infocom Research Singapur'da da gene araştırmacı olarak görev yapıyor. Ve aynı zamanda 2 tane startup'ın da yönetim kurulunda ve danışma kurulunda görev yapıyor. Araştırma konuları Internet of Things, Pervasive Computing, Blockchain, Crowdsourcing, Data Analytics, Privacy ve Security konularında araş yapıyor. 170'ten daha fazla peer-reviewed yayını, makalesi bulunuyor ve birçok konuşmada bulunmuş. Kendisi bugün bizlerle Blockchain for Cyber Physical Systems, Applications, Opportunities and Challenges adlı konuşmasını paylaşacak. Ben kendisine bırakıyorum.
Thanks.
Okay. Thank you, Murad, Jamal, and Husnu for having me here. It's my great pleasure to talk about some of the interesting research that we are doing in my group. So, yeah, as Murad said, I come from Sydney, quite far. I just got here yesterday morning, but I've slept well, so I'm okay with jet lag and stuff like that. So, of course, this work would not be possible without a team. So I would first like to acknowledge a large group of people I won't name everyone here, but so there's a bunch of students I have and colleagues at UNSW. There's a collaborator at CSIRO, TCS. We have some collaborations with TU Graz in Austria, also PU CRS in Brazil, and very recently we're also working with some folks in University of Oulu in Finland and University of Zurich. Okay, now a warning, you'll find a lot of comic strips interspersed in my talk. I try to sort of make things a little entertaining, if you may. Okay, so you'll see some Dilbert comics being shown. And I'll just give you a few seconds to just look through that slide, and hopefully some of you will laugh. Okay. Okay, but that's sort of just highlighting the issue with blockchain, right? It's everywhere. It's being touted as the next big thing, and it's going to solve all our problems. But what I'll try to do here is give you some context and tell you some of the research we've been doing on how we can use blockchain, particularly in the context of cyber-physical systems, right? So what exactly is a cyber-physical system? If you haven't heard this term, it's sort of, as it says here on the slide, we are bringing together the physical world as we know it. And by the physical world here, we mean everyday objects. So down here, you see essentially everyday objects like sensors, your mobile devices, your smart appliances, even cars, trains, smart grids, buildings, all being connected to the internet through the Internet of Things as we know it, right? And the key point here is all these devices will be sending some information back to the cloud, essentially, where the virtual world comes in. And then this information will be analyzed, and somehow, hopefully, that leads to some informed actuation, whereby this information can then be used to close the loop. The idea being that we want to take humans out of the simple loops and let the devices sort of work by themselves, interact by themselves, hoping to improve our quality of life, right? And there's a wide range of application domains here, ranging all the way from autonomous vehicles, smart grids, smart spaces. So the opportunities really are endless, and we're actually seeing a lot of this actually happening in real life as well. Now, of course, underlying all this is, sorry, not the Internet of shit, I should say the Internet of Things, right? So we have a lot of devices in our environment now being connected to the internet. And I'm sure you've seen graphs like this where they track how many devices are now being connected. So we are roughly here. So I would say roughly about 50 billion devices, give or take a few, are now connected to the internet. And many more, sorry, many more will be as we move forward, right? So that's one sort of driver. The second driver, of course, is what do we do with these things? We collect data, right? So that's where we have this flood of data that's going to happen. These are just some numbers to throw around. So a typical autonomous vehicle is expected to generate over 4 terabytes of data in one day. Okay, so just think of the volume of data that we're talking of, right? So clearly there's a lot of data, and we need to make meaning out of that data. It's not just enough to collect this data anymore. We need good data analytics. And now if you look at the current IoT ecosystem, right, if you take any typical IoT product these days on the market, you'll find it kind of follows this sort of 3-tier architecture. So you have this small sensor device, which is collecting some data. It's talking to some gateway. It could be a hub that you install. Say, for example, Samsung has this smart things concept, right, where you install this smart thing hub, put a bunch of sensors in your house. All these sensors will talk to the smart things hub, and then the data will be sent back to the cloud where it would be processed. Or you could think of, say, a wearable like what you wear on your wrist, which talks to your mobile device, and then that connects to the cloud. So you have this very typical sort of IoT ecosystem. And the issue with this is, yeah, this is all fine to get things bootstrapped, and it has its applications in certain spaces, but we are eventually going to hit a point where this is going to not scale, right? If you're talking of really 100 billion devices connected to the internet, we perhaps need to move away from this centralization concept because everything sort of gets connected through the cloud servers. And it may so happen that sometimes these cloud servers break down and then you can't use these devices anymore, right? So they're clearly a bottleneck. They're a central point where attackers can actually attack the network, which has been happening a lot these days, where some of these cloud servers get attacked, all your data gets compromised, and it's out there, right? So this is quite important that we sort of think about this centralization, and perhaps if we can break away from this. Another reason to break away, perhaps, as I already hinted, is the security and privacy implications, right? So some of you may have seen these news articles where they talk of this Mirai botnet. Essentially what it is if you buy any IoT device off the shelf, right, you have a default username and password, and 90% of the people do not bother changing this username and password, right? So once you install these devices, if external attackers try to attack your network and use these passwords to log into your these devices, they can easily install malware on these devices, and that can lead to a massive denial of service attack. So there are actually a lot of examples. So these are some numbers from a couple of years back. So there's this blogger called Michael Krebs who writes about security, and his particular website was targeted with a denial of service attack, which created a volume of over 665 gigabytes of data per second. Okay, that's the amount of data that was bombarded on his particular web server, right? And this was all generated using webcams, so off-the-shelf webcams. So yeah, this is clearly a problem. The IoT devices are exposed. It's not too difficult to hack them. And if you think about it, if you're talking of critical infrastructure, say like vehicles or smart grids, right? And if people compromise these devices, then we are playing with our lives essentially, right? So there's this very famous hackers who actually showed that you could hack into a moving vehicle. In this case, they used the Jeep Cherokee as an example, and they were able to take over the control of the vehicle from the driver. I won't play you the clip here, but you can find this on the internet, right? So this is quite serious. I mean, we are talking of potentially people using their lives if if attackers really got access to these devices. The next problem is the issue of data siloing, right? So we give over a lot of our data. I mean, Google, for example, it knows a lot about each of us here, right? Because we use Google services. Perhaps some of you use Facebook. So again, the same issue, they're collecting a lot of this data. And we really don't have a lot of control over this data, because once the data is with these providers, they really can use it for whatever they want. A prime example is all this recent fiasco that happened with Facebook, right? So, I mean, you've seen this perhaps in the news, just trying to make the point that we have to be careful about how our data gets handled. And this is particularly quite serious now because we are talking of IoT data, right? So these devices are in our environment. They're collecting a lot of information about us, how we interact with the environment, and so on and so forth, right? So you can actually build a full picture of what a person does over an entire day, over weeks, over a year, and that data could potentially be harvested for devious purposes as well. So what are the challenges that we are facing when it comes to cyber-physical systems? So first of all, there's a lot of heterogeneity in the devices. By that I mean the devices have very varying capabilities, right? If you talk of a small motion sensor that might be here in this room, it's got very low hardware. It's not going to be able to do a lot of computation. In contrast, if you take your mobile phone, it's quite powerful, right? So you have this wide range of devices, and it's very hard to come up with a singular solution that would always work across all these devices. So we must sort of appreciate the fact that we need to take this into account when we design our solutions. Next, we have the issue of multiple attack surfaces, because again, when it comes to billions of devices, if you even compromise 0.1% of the devices, you already have a large number of potential attack points into the network, right? So that's very important that there's no sort of weak link in the entire chain. Oh, sorry. Then, of course, the issue of scale. Looking at this from a perspective of a solution, whatever solution we propose must scale, okay, and be able to handle these billions of devices. I already talked about the issues with centralization, so it would be preferred to have a solution that's perhaps more distributed. The issue about data, and then if you look at all the products that are currently on the market, there are very poor implementations of security protocols. There are various issues leading to different operating system stacks and so on and so forth. So all of these are huge challenges that we're facing. So about 2 years back, we've been working on IoT for quite some time, frankly, but we started sort of taking a step back and started looking at this problem and thinking of how we could perhaps solve these problems, right? So I'm this big giant ape here that you see. And of course, my students had a brilliant answer. They said, okay, why not look at blockchain, right? Because that was emerging about 2-3 years back. It was out there. So we started looking at perhaps how we could use blockchain to address some of these problems in cyber-physical systems. So before I get into some of the things that we've done, I may just take about 5 minutes just to give you a brief primer on what blockchain is, okay? Because I don't know if everyone in the audience has some insights about that. And I'll use Bitcoin as the example because that's perhaps the most widely known implementation of a blockchain. So how does Bitcoin work? Well, it's a very simple concept. If let's say you have one person, Alice, wanting to send some money to Bob, Alice would create a transaction. Essentially, it's just sort of like a message. The message would contain information about how many Bitcoins Alice wants to transfer to Bob. And then this transaction would be signed by Alice. And that's the most important thing here, because Alice is sort of certifying that she is actually sending whatever Bitcoin she wants to Bob. And then this transaction gets broadcast to the entire network. So the key point here is this is a distributed network. There's no sort of central server. You have multiple nodes in the network, and each node can create a transaction and broadcast it to the entire network. Now, the important point here is once you have these transactions out there, they must get added into the actual ledger or the blockchain as we know it. And in order to do this, there are certain selected nodes who take on the responsibility of verifying these transactions and adding them into the blockchain. So these nodes are known as miners because this whole, just from the play of words essentially, because they're mining some information into the chain. And in order to mine this information, they must solve a problem that is cryptographically hard, but very easy to verify. And why must we do this? Because remember, this is a distributed network. And in order to reach consensus, we must have a way whereby some arbitrary nodes with malicious intents cannot get control of the entire blockchain. And moreover, this process should be randomized so that there's no one single entity which controls the entire network. So that's the reason we use something complex for doing the actual mining. And in Bitcoin, one particular implementation of this instantiation of this idea is this whole proof of work concept, right? So the miners need to solve this complex problem. One of them will win, not all will win. And then the winner gets to actually take these transactions, create what's called a block of transactions, essentially a combination of these messages. And then this block gets added into the blockchain. And this happens roughly every 10 minutes. And in return for this exercise, the miners get a reward. So they get some Bitcoins essentially for doing the mining. This new block then gets broadcast to the entire network, and then all the nodes, because this is a distributed network, remember these miners, each of these miners is keeping a local copy of the blockchain. So this new block can then get added into the blockchain. Now, on occasion, because this is a large distributed network, on occasion you'll have instances where there may be some conflicts, and this leads to what is called forks. But over time, these forks sort of, you kind of come up with a clear winner, and then the forks are sort of just left as they are, and you follow the longest chain, essentially, in the network. And once a transaction is sort of 3-4 blocks deep into the chain, it sits there forever. You can't reverse it, essentially. Okay? And then, of course, from the perspective of the end users, you have essentially like a wallet. It's just a digital wallet on your mobile device, for example, where you can keep track of your Bitcoins and all these transactions that are processed. Okay? And there are ways, essentially, in Bitcoin to avoid something called double spending, where a person might send the same transaction to multiple people, essentially, trying to cheat. Yeah. So that's just Bitcoin sort of in two minutes, essentially. Now, going a bit deeper into the actual structure of the blockchain, right? So as the name suggests, it's a chain of blocks. So each block essentially is a set of transactions. Each transaction can have certain inputs and outputs, and there are various fields indicating various semantic parameters in these transactions. And these blocks have certain important header fields, which essentially in this case is a hash of all these transactions that are stored here, and a pointer to the previous transaction in the chain. So that's essentially what establishes this chain across these multiple blocks. Okay. I talked briefly about the proof of work. I won't get into the math here, but essentially here a miner must find a certain nonce such that the hash of the block contains a certain number of leading zeros, and this is actually very complex to do. And the complexity and the difficulty can actually be varied depending on how many leading zeros you have in this problem. And that can be controlled in the network. Now, if you look at the actual transactions, right, within a particular block, now the question is, how might you store them? Of course, you could just create a simple chain of all these transactions, but a more efficient way of doing this is to use, sorry, wrong slide, okay, is to use what's called a Merkle tree. And of course, I don't mean this Merkle tree, I mean this Merkle tree. Okay, so in this Merkle tree, the leaves essentially are the transactions. And what you do is you take a hash of these transactions, and typically you would just have a binary tree. So you take the hash of the leaves, that gives you these hashes, and then you sort of concatenate 2 hashes at a time till you get to the root hash, right? And by having this structure, it's very easy to now check if a particular transaction is part of the blockchain, because for example, if you wanted to check if this transaction is part of the blockchain, you would simply need this particular hash, this hash, and that would allow you to do a quick check without requiring this branch, essentially, of the tree, right? So that's a very quick way to check if that particular transaction is sitting in this particular block. Okay, so what are the salient features of this whole concept of blockchain? Well, firstly, it's a distributed network because there's no one central server. There's no concept of a server at all, essentially. It's a distributed network. All the nodes are storing the blockchain, a local copy, right? And they're all involved in some way in the process of verifying blocks and adding blocks into the blockchain. Another important feature is that all the information is timestamped and arranged chronologically. So they're actually added in order, which is again important, particularly when these transactions have dependencies with each other. The third important feature is the fact that this data cannot be altered. So it's immutable, right? So once some information gets added into the blockchain, it sits there forever. No one can change it, right? And as a result of that, what we have is we can use this blockchain at a later point in time to check something from the past. So that gives you the ability to audit the blockchain, which is also quite important. Okay. And finally, the transactions and even the blocks are all digitally signed. So that gives you the assurance that the blocks and the transactions were not modified. And it's also important for non-repudiation. So later in point, you cannot say I didn't sign the transaction because your signature is in there. So it can actually be used as proof to confirm that you were the one who actually signed this transaction. Now, in terms of the categories of blockchain, broadly speaking, you have sort of two broad categories. So the Bitcoin blockchain that I talked about was what's called a permissionless blockchain, which means anyone can essentially join, right? So anyone in this room can actually be part of the Bitcoin blockchain if they wanted to. It's open to the public, right? The users are anonymous in a way. And a result of this is that because we have this open blockchain, it means that we need to be a bit careful about how information gets added, because you don't want malicious information to get added into the blockchain. As a result, the processes used for verifying and adding information into the blockchain are slow, okay? Because we have to be careful. There is no concept of trust. This is a trustless network, completely trustless. You do not trust any other node in the network. The consensus algorithms, as a result, are quite complex, kind of going back to this point I raised. So proof of work, which I already talked about. There are other implementations like proof of stake, proof of importance, and so on and so forth. Okay, but I won't get into all the nitty-gritty there. And some concrete examples, of course, you have Bitcoin, you have Ethereum, and a few others like IOTA and so on that you see there. In contrast, you have what's called a permissioned blockchain, right? So this is very different. This is a closed, essentially, blockchain in that only authorized nodes can be part of the blockchain. Okay? All the users are known, they are identified. And as a result, it gives you some assurance that it's very unlikely in this case that malicious nodes would be allowed to join the blockchain in the first place. So the processes, underlying processes for adding information into the blockchain and so on can be quite fast, unlike permissionless blockchains. As a result, the consensus protocols are also quite simplified. So you have simple protocols like Byzantine fault tolerance or POET, which is essentially based on time, the concept of a random time. And some concrete examples would be, say, the IBM Hyperledger, for example, or Ripple, Coda, and so on and so forth, right? So now, given this, the question is, which kind of blockchain would you use, okay? And that's, there's a very nice paper, actually, we found that came out last year, which kind of comes up with this very nice flowchart, essentially, of the decisions that you need to check in order to decide which type of blockchain you might want to use, right? So for example, let's say, first of all, the first question you want to ask is, do you actually need to store state in your system? Assuming this is a yes, then you would check if there are multiple nodes that would be writing into the database, essentially. Then you would check if there's a trusted third party that you can trust, who can take control of the network. And assuming the answer for this is no, then this is critical. Then you need to check if the nodes that are writing information into the blockchain are known or they're anonymous. And then if the answer was no, you would go with a permissionless blockchain and so on and so forth, right? So it's a nice exercise to look at something like this. It gives you some intuition as to whether the use of blockchain is actually right for your particular problem. Okay, I'll take a short breather while you look at this cartoon. Okay. Okay, how am I doing on time? Yeah, okay. Okay, so now let me get into some of the actual research that we've been doing. So far, I've just given you a brief introduction. So first, I'll talk a bit about the work we have been doing in the Internet of Things, right? And I'll give you a very simple sort of motivating example. So let's say in my house, I've installed a camera, essentially, which checks if a particular person is at the door. And assuming the right person is at the door, it would trigger a smart lock on my door to open the lock, right? So if it sees that it's me, it will instruct my lock to open, and then I would be granted entry into my house. Now, let's say for some strange reason, the thieves find out I'm here in Turkey today, right? They know my house is, no one's in my home, and they decide to rob my house. Right? And let's say they are indeed successful, right? They somehow get access to my house and they rob me. Now, the question is, who is responsible, right? Was it the camera that failed? Was it the lock that failed? Or was it something the burglars actually did that circumvented what these two devices were doing and allowed them to break into my house, right? So if I go back, day after tomorrow, I find my house is burglarized, who do I blame, right? Now the point here is, okay, the manufacturer of these devices because it's actually owning all this data, right? So it's got all the screen captures of the images that it stored. If they were responsible, somehow their system malfunctioned, who's stopping them from actually changing the data? Because the data is with them, right? How do I know that they didn't manipulate the data? And the same applies to this smart lock. If they were at fault, they could very easily go and change the data that's stored with them, and then you won't be able to implicate them because they fudged the data. So I think this is a good example where something like a blockchain could help, because all the interactions could actually be stored in the blockchain, right? So whenever this camera sees someone, it could create a transaction and log that into the blockchain. So we have now a timestamped record that this particular image was captured at this time, and this is now being confirmed and stored in the blockchain. Similarly, whenever the smart lock opens, it could actually create a transaction and store it in the blockchain. So again, we have a timestamped record of when the blockchain was, when the door was actually opened, and that stays in the blockchain. So going back to my example, if my house was indeed burglarized, I could now go and retrieve these transactions from these two devices, check what went wrong, and I would be completely assured that no one actually fabricated the information, because it's now been confirmed by other nodes in the blockchain, and it's sitting there forever, right? So I think that's a good example, essentially, to motivate the reason for having something like a blockchain in the context of IoT. Of course, this doesn't mean that you can just take something like Bitcoin and make it work in the IoT context, because that won't work. There are certain unique features that IoT presents which make things a bit more interesting, right? And also gives us opportunity to do some research. So firstly, the consensus algorithms that are used in something like Bitcoin simply won't work on an IoT device. I mean, imagine these devices having to solve a proof of work problem in order to add data into the blockchain. That it's just not going to be capable of doing that. Secondly is the overheads, because something like in Bitcoin, for example, everything is broadcast. So you have a completely decentralized network. So again, that won't work in IoT because you could have hundreds, millions, billions of devices in the network. The third issue is latency, right? In Bitcoin, when you send someone, say, some Bitcoins, it takes about half an hour for that transaction to be actually verified, logged, and confirmed. And only after half an hour do you really know that this process of sending the money actually went through, right? Now, you can't have a half an hour delay for a door opening when it sees you, right? That just simply doesn't work in the IoT context. So we need something that is very fast, that can handle transactions at a much faster rate. Similarly, we need a network that has high throughput. Now, with Bitcoin, we're already seeing some problems with throughput. This is a known problem. The Bitcoin network has been shown to have very limited throughput because you can only sort of verify about 7 transactions per second, right? So this again won't scale in the IoT context. And then some of the complexity that's added in Bitcoin, say for example, to prevent double spending is simply not relevant in IoT, because in these examples, we are not really talking of money. We are just talking of interactions being stored. So you can't really double spend an interaction, right? So some of those mechanisms could actually be removed from the network, from the blockchain. And then the issue of incentives is still quite important, because in this context, again, because there's no money being exchanged, the question is, how do you incentivize nodes to actually participate in the blockchain? So that's still an open problem, I would say. So next, I'll present you in about a few minutes just a quick high-level overview of some of the work we've been doing in this regard. And we have this concept of what's called a lightweight scalable blockchain for IoT, right? So what we have essentially done is tried to address some of these issues and come up with a simplified approach. So as in any blockchain, we still assume there's an overlay network, essentially a distributed network, which is comprised of your IoT devices, your gateways, your cloud servers, your service provider servers, and so on. And what we assume is that these nodes would sort of organize themselves in some clusters, and we have certain cluster heads who would actually be responsible for managing the distributed ledger. So again, unlike a traditional blockchain where all nodes participate and are sort of involved, here we have a tiered approach, essentially, where some of the low resource nodes could sort of just be part of the clusters and not actually participate in all the complex processing that's needed to manage the blockchain. And then we come up with a number of optimizations to sort of fit the IoT context. So we have a very simplified consensus algorithm. We have this notion of a trust mechanism, which can help us in reducing the processing time for the transactions. And we also have a mechanism which can adjust the network throughput, which sort of avoids the issue which Bitcoin faces, for example. Okay. Now, some of this work is all being published. You can find some of these papers. Feel free to email me. I can send you copies, or you can find them through Google as well. Okay, so digging into this a little more. So firstly, we assume that there's a clear separation between the data flow and what we call the control plane, essentially. So the data flow is essentially all the sensor data that's flowing. The control plane comprises of all the messages that are involved for managing the blockchain. We also assume that the actual device data may not be stored in the blockchain, and that's simply to ensure that the network scales. So we assume that the actual data is stored perhaps in the cloud, or maybe in a local server, let's say in a smart home or a smart building. And we only store pointers, essentially, references to the data within the blockchain. So that allows us to keep the size of the blockchain to something that's manageable. Okay. For example, if you look at the Bitcoin blockchain, it's over 100 gigabits now. So before you even start participating, you have to first download all that data and before you can become part of this blockchain. So we want to avoid those problems here. The cluster heads are what we call the overlay block managers, and they are mainly responsible for all the blockchain processes, essentially the generation of blocks or transactions, the verification, the storage of the transactions, and also access control. So the OBMs are essentially, if you may, the miners in our network. And the network would look something like this, right? So you have sort of resource constrained devices acting as the children in the cluster. You have certain more capable devices acting as the cluster heads or the OBMs. And these OBMs form the distributed network. And these are the clusters that each OBM is responsible for. So that's the two-tier architecture. And we could even extend this to multiple tiers, essentially, if required. As with Bitcoin, we assume the nodes are given a public-private key pair, and the public key is what's used to identify a node. And if privacy is a concern, just like Bitcoin, we could have changeable keys. So you could use different keys for each transaction. The transactions are signed using strong hash functions like SHA-3, for example. And we have two types of transactions, some that only need the signature of the transaction generator, some that need signatures of both the generator and the recipient of the transaction. And we assume separate transaction ledgers per node. And this picture sort of gives you a view of what the transaction actually looks like. So you have the ID, which is nothing but the hash of all the information in the transaction, the hash of the previous transaction, which creates the actual chain, the public key and the signature of the requester, similarly the key and the signature of the requestee, and then some additional information down here, which I won't get into. Now, of course, one issue is how do you limit spam accounts, right? Because again, this is a public blockchain. So what prevents some malicious entities from joining the node and sort of creating fake transactions and taking over control of the network? So for that, we propose kind of two approaches. One where we assume that the keys that you're given are actually verified through some sort of certificate authority. Or we assume that in order to create this initial transaction, which is called a genesis transaction, you would need to burn certain coin in the Bitcoin blockchain and then create a link to that particular transaction, right? So which means there is some effort involved on the part of the entities to actually join the network. And this sort of allows us also to verify that someone else has actually verified the identity of the nodes before they participate. So this gives us some assurance in terms of which nodes actually join the network. And then to support various interactions in the context of IoT, we do present a sort of extensive vocabulary of transactions. So of course you have the initial transaction, which is called the genesis transaction, that just to start the ledger. And then you have a range of transactions depending on what you want to do with the IoT devices. So if your device is storing data in the cloud, it creates a store transaction. If someone else is accessing data from your IoT device, they could create an access transaction. If someone wants some real-time information from a particular device, you could create a monitor transaction and so on and so forth. And the flow of these transactions is actually distinct from the data because transactions are broadcast, whereas data does not need to be broadcast. So that allows us to create that separation. And you could also have smart contracts, right? So smart contracts essentially are programmable contracts where based on certain conditions, you could take certain actions. So you could have this sort of if this, then that interaction. So if a certain sensor gives you a value, say someone opened the door, you could then ask the light to turn on, for example, right? So those sort of simple interactions could be manifested using a smart contract. Now, an important part of all of this is the access control, because remember with IoT devices, we have the issue of sort of malicious nodes getting access to the devices themselves and potentially putting malware on them. So to prevent that, we use a simple idea of access control list, essentially, whereby the cluster heads or the OBMs maintain this access control list, and only if certain fields match, only if the requestee PK pairs match, those particular transactions are actually sent to the actual nodes. So this sort of prevents someone from, say, bombarding a device with random transactions or also injecting software, fake malicious software into these nodes. For consensus, we've just used a very simple idea. This is not very different from the POET protocol, the proof of elapsed time protocol. The idea being that within a particular consensus period, only one node can only add one block into the network. And each node sort of waits for a random time before creating this block, which prevents, say, one particular node from taking control of the network. And this new block is, of course, broadcast to all other nodes who then need to verify the signatures on these blocks. And if a node does not comply, then those particular blocks are simply dropped, and the trust associated with those blocks is also decreased. For verifying the blocks, we leverage the trust that the nodes have built up in each other. Now, normally you would want to verify all transactions in a particular block, but clearly that takes up a lot of time. So as a compromise, we say, okay, if we have trust in a particular node, we will only check a fraction of transactions in the block. Okay. So you could imagine something like that. Now, those numbers don't necessarily mean anything, just an example. But let's say if a node has built up some direct evidence, which means if you've actually verified a transaction for another node, you can have some direct evidence about that node. So progressively, as nodes build up trust in each other, they need to validate fewer transactions within a particular block. So that allows us to speed up the verification process. And finally, to handle the issue of throughput, we actually have a mechanism whereby we can tune certain parameters in the network to make the network scalable to the transaction load in the network, right? And the intuition for this kind of can be explained through this particular equation. So let's say Tmax is the maximum number of transactions in a particular block, and let's say there are m OBMs in the network. So which means the total number of transactions that you can actually add into the network is the product of Tmax times m. And the numerator here shows you the total load in the network, which is essentially the number of nodes in the network times the rate at which they're generating transactions times the actual duration of the consensus period. So the nodes could actually monitor all of these parameters and compute the utilization. And if they find the utilization sort of goes beyond certain thresholds, they could actually adjust the consensus period. So they could reduce or decrease the consensus period, or they could reduce or decrease the number of OBMs in the network. Now, of course, this is easier to do. This is much harder because it needs reclustering. So this is a preferred option, and we would only fall back on this if this can't be adjusted anymore. This picture is showing you the flow of transactions in the network. So let's say we have a smart thermostat in the network, and let's say the smart thermostat is storing data into the cloud, right? So for this, we create a store transaction, which is initially signed by the smart thermostat. It's received by the cloud storage, and if the cloud storage agrees to store this data, it would sign it, and then this transaction gets logged into the blockchain. Similarly, let's say if it's some external person who wants to access, say, the historical data that's stored by the smart thermostat. Let's say this is the service provider of this company that manufactures the smart thermostat. So it could send a request transaction to the blockchain, and this request transaction is initially just signed by the requester. Now this transaction gets broadcast through the network till it actually reaches the cluster head, which is responsible for the smart thermostat. And when it finds a match, this cluster head would then send it to the actual smart thermostat. Now, assuming the thermostat is okay with this request, it would then sign the transaction, here, and then the transaction would be logged into the blockchain. So at this point, we now have a record that these two entities have agreed that data from the smart thermostat would be provided to the requester. And then this data could directly be sent to the requestee. You don't have to go through the blockchain for that. So that's just a simple example of how this would actually work. Now, in our papers, we have done a very rigorous security analysis. I won't go through all of that in here, but just to give you a sense, we have shown that you can meet all the basic requirements for security. So, for example, if you wanted data to be confidential, you could actually encrypt the data that's stored in the cloud or the local storage. Integrity is kind of naturally provided. because the transactions are signed, and these hashes are cryptographically strong, so that assures you of integrity. To handle availability, the cluster heads or the OBMs, they would only allow transactions to go through if they meet the access control list requirements. So this ensures that a particular node cannot just be bombarded with a large number of transactions. And so on and so forth. I won't go through all of them, but that's just to give you a brief look at the security analysis of our work. Okay. Now we actually have, we are very close to coming up with a full implementation of this particular framework. And for that, we are using Raspberry Pis essentially as the IoT devices. But we are yet to do a full comprehensive analysis. So in the meantime, we have some simulation results that we have generated just to show how this all would work. And in the simulations, we've sort of simulated a smart home scenario. And we've also simulated the actual overlay. And for that, we've used a network simulator. So in this overlay, for example, in one particular scenario, we've set up a 50-node network with 13 OBMs and say 5 requesters generating 4 transactions per second. And this slide is sort of showing you the effect of using the idea of distributed trust, right? So in very simple terms, the idea being that as the nodes build up trust in each other, they only need to verify a small set of transactions within each block. So this shows you the evolution of time as time moves by. And this shows you the processing time required to validate each block, essentially. Right? So initially, as you'll notice, the blockchain sort of, when you don't have trust, the amount of time required to verify the transactions is the same as, say, a baseline, which is where you would be verifying all the transactions in the block. But as time passes by, the nodes actually build up trust in each other. And as a result, this axis is showing you how many transactions you're actually verifying within a particular block. So initially, you would verify all the transactions, but with passage of time, you would now be verifying, say, fewer transactions. And as a result, you'll see that with our scheme, the amount of time required to verify a particular block is lower than if you were verifying all the transactions. I mean, this is kind of intuitive, but this is just giving us a sense of how much we can save for processing a particular block. I'll skip this particular slide for the sake of time. So that's the initial idea that we came up with of proposing this lightweight scalable blockchain. But then we were starting to look at this this whole concept of what's called a sensor as a service, or say this whole idea of a IoT marketplace, right? And so currently we're extending this idea to kind of look at scenarios where the data from IoT devices could potentially be traded to, say, people who might have interest in this data, or say the actual service that's provided by a device could be traded to another entity that might see need for this. So just as a small simple example, let's say there was a smart plug here in this room, and I'm realizing that my mobile phone is dying. It's running out of battery, right? So if I could quickly plug my mobile phone in there, and for this charging interaction, if my phone could pay, say, a few cents to that particular wall socket, that could be considered as a trade between these two devices. So we have actually come up with this particular framework whereby IoT devices could actually trade their services or data with interested consumers, right? And so for this, we actually sort of need 3 different things. So firstly, we need a distributed ledger to manage the actual trading transactions. Essentially, the buyers need to place an order, the sellers need to sort of announce their services and invoice the buyer. So all that is taken care of by this distributed blockchain here. We also need the payment infrastructure. So this could be managed by, say, using a cryptocurrency, say like Bitcoin or something like that. And then finally, we need the actual data exchange to happen, and that's taken care of by using standard TCP/IP protocols. So that's something that we're kind of pushing forward. And if you're interested, I can pass you some of our papers on this as well. Okay, so again, a short breather before I move on to the next part of the talk. Okay. Okay, so next I'll briefly talk of our work in connected vehicles. So far we've been looking at IoT. Next, since this graph is sort of highlighting the fact that autonomous vehicles or smart vehicles essentially are now on the rise. And there's this huge trend that's happening, and we're kind of at a juncture where this will suddenly start picking up, and in a few years you'll see these actual smart or automated vehicles being driven on the roads, right? And as I kind of hinted earlier, these autonomous vehicles are actually instrumented with a large number of sensors. So you have sort of LiDAR sensors, you have GPS, you have cameras, a bunch of sensors that are creating a lot of data. And it's anticipated that each vehicle would create up to 4,000 gigabytes of data per day, right? So now the question is, how do we manage all this data, right? And particularly, if you look at some of these recent incidents that are happening, right? Like you have these autonomous vehicles that are being tested on the roads, and some of them have actually caused accidents, right? Where they've hit other cars or hit other pedestrians. And this is eventually going to be a reality. Certainly, autonomous vehicles will save a lot of lives because of these smart controls, but at the same time, there will be occasions where you might still have accidents, right? So a few months back, together with my collaborator, we wrote this article about who's to blame when driverless cars actually have an accident. So we started looking at this problem of vehicle forensics, essentially liability attribution, right? So if you have an accident, who is responsible? So there are different angles to this. So firstly, there could be a problem with the actual vehicle itself. You might not have updated the vehicle, or for some strange reason, the software is behaving in a manner that's not consistent. So in those instances, the auto manufacturer may be the entity to blame. In some instances, say the car was taken to service and the service technician did something wrong and caused the vehicle to to malfunction. So in that case, the liability rests with the service technician. Or in some instances, it might just be the vehicle owner who didn't follow the instructions. Perhaps the vehicle owner didn't update the software or didn't drive as expected, and that caused the accident, right? So in this regard, we again think that blockchain could be a nice way to solve some of these issues, because of, again, the same reasons being that this is a distributed network where all the data that's added is immutable and remains there, and it's trusted, right? So just to give you a high-level overview of how this would work, we've come up with this framework where we propose to have sort of different partitions. So there's this operational partition down here, which captures all interactions that happen with the car and, say, the service technician and, say, the insurance company, right? So these interactions are sort of recorded in this operational partition, and this partition is distinct from the other partition, which is called the decision partition, where all the decisions for attributing the liability are actually handled. And the decision partition is comprised of, say, the legal authority, some government transport organization, and the auto manufacturer, right? So we've also proposed a transaction vocabulary to support all these interactions. So for example, if the vehicle suddenly slams the brake, or if it records an actual collision, so the information from the vehicle sensors gets bundled, and captured into what's called a safety evidence. And that safety evidence gets logged into the blockchain. Okay. Remember, here we are not talking of normal activity. We are only talking of abnormal activity. So the rate at which these transactions are generated are not going to be that high. It will only depend on the instances where something goes wrong with the car. And then we have the primary evidence transaction, which actually records some data describing the accident, because when an accident actually happens, the vehicles on the relevant devices will be capturing a lot of data about these transactions, about these accidents, sorry. So that gets logged in the primary evidence transaction. Next, we have the notification evidence transaction, which records interactions between the manufacturer and the service technician with the car. So this is what would represent, say, a software update or some service that the technician did on the car. And then we have some transactions that records the response of the actual vehicle to these transactions. So whether or not, say, the update was actually correctly installed on the vehicle, that could get logged as an execution transaction. And finally, we have support for, say, entities from the decision transaction to actually query information that's logged in the blockchain for the purposes of, say, an investigation into the accident incident. So to give you a quick example, let's say there's this 3-vehicle accident that happened here, down here. So each of these vehicles would now create a transaction which contains all the sensor data that is relevant about this accident. So this could be things like, say, a video feed, information from the car sensors, the speed at which the car was driving, so on and so forth. And all that would now get logged in the operational partition. And here, for example, it's showing you multiple operational partitions, because the actual manufacturer might be different for these vehicles. So we anticipate there could be sort of multiple operational partitions made up of multiple auto manufacturers, multiple insurance companies, and so on and so forth. Finally, these transactions, once they are created, they need to be verified. So this is the verification that happens. And since this is a permissioned blockchain, we can actually have a very simple consensus mechanism to handle this. And then, say, at a later point in time, once this accident has now been investigated by the legal authorities in the decision partition, they could then query the information that's stored in the operational blockchain by sending this request, essentially, to the auto manufacturer and the insurance company to retrieve all this data. And then they could make a decision based on whatever information is available and attribute the blame to the appropriate entity. So that's just a quick sort of high-level view. If you're interested, I can refer you to our paper, which goes into more detail. And lastly, I'll talk about supply chains. Okay, so this is another interesting area. And the reason we are looking at this is because particularly we are looking at this from the perspective of food supply chain. So you might have seen some of these recent incidents where something went wrong. For example, there was horse meat that was found in certain burgers. There was this salmonella outbreak, which was caused due to some issues with some papaya fruit from Mexico, and so on and so forth, right? And it actually took about 2 months for them to investigate which particular farm was the sort of entity that led to this particular outbreak. So I think this also presents a nice example where blockchains could actually work. And if you look at supply chains, right, they're actually made up of a range of organizations. So you have, say, the entity that's producing the raw material, which gets picked up by a supplier. This supplier then sells it to a manufacturer. The manufacturer would assemble different raw materials, create, say, the product, let's say a box of chocolates, for example. And then the products are sent to a distribution center, which then sends it to the retailer, and finally the consumer buys the actual product, right? So it's actually a whole chain of entities that are actually involved. And if you look at the state-of-the-art traceability systems, you'll find that a lot of this information is just siloed. So the manufacturer will have certain information about the product, but it won't actually, you won't be able to connect that information, say, with the information from the supplier and the information from the distributor. So they're all separate, sort of siloed databases which do not talk to each other. So it's very hard to go and pull out information from all of them and link them together. Okay. Moreover, there's chances of mishandling, false data being entered because no one is actually verifying some of this information. And most importantly, there's no way for you as a consumer to actually go and pull out information from all of these entities. So imagine, let's say you wanted to find out in your box of chocolates where the cocoa actually came from. So there's no way for you to actually find that out at the moment. So how can a blockchain help? Well, all the origin information of the raw material, right? So once the raw material is actually picked up from the creator, that could actually get logged in the blockchain. Secondly, all these handovers could also get logged. So whenever, say, the raw material is delivered to the supplier, that particular interaction could get logged, and so on and so forth. Thirdly, if you have certain IoT data that are, say, installed on the farms or installed somewhere along the supply chain, say, for example, the distributor is keeping track of what temperature this particular food item is being transported. So that IoT data could also be integrated into the blockchain. And finally, there are certain hazard and what's called as the HACCP standard. So this is a standard to verify if something goes wrong in the handling of the food products. All of that can also be achieved by the fact that this information is actually stored in the blockchain. A consumer can query the blockchain and retrieve the entire ledger. So you could actually see the entire flow of how the item made its way from the point of origin to the actual retailer. So that would potentially also be possible. And then in instances where there are some problems, there's, say, an epidemic due to something wrong with the food product, you could again retrieve all this information very quickly from the blockchain, unlike current instances where it can take up to 2 months to get this information. So what we are proposing is a permissioned solution here, because again, there's no need for this to be open. We have certain known entities which are writing information into the blockchain, right? The difference being that we don't want one particular entity to have control over this permission network. So for that reason, we propose what's called a consortium blockchain. So we have a number of entities like, say, the Food Control Authority, say government organizations, say the technology provider who's actually going to implement the blockchain, form what's called a governing board. And then this board is now responsible for managing the blockchain. And this board will also set certain access control rules indicating who can add information into the blockchain. So essentially, this is a very controlled environment where only certain entities can add certain types of information. So for example, if you're a participating entity, going back here, all these entities are what we call participating entities. A customer, for example, is a non-participating entity who only wants to read information. And these participating entities would be writing different kinds of information into the blockchain. So for that, we create this nice access control list. I won't get into the details here, but just giving you a sense that only certain entities can do certain things in the blockchain. So it's a very controlled sort of environment. And we actually propose a 3-tier network architecture. So this works as follows. At the bottom layer here, we have all the FSC participants and also, say, the non-participants. And then the actual blockchain, rather than having just one global blockchain, because remember, supply chains span across the globe, right? So your product might be manufactured, say, in Australia, and it might be being shipped all the way here to Turkey. So what we envision is something like what's called a sharded blockchain, where you create separate side chains, and each side chain, say, could cover one geographic region. And these side chains maintain their own local blockchain, okay, which is synchronized locally within these side chains. Now, for managing the blockchain, again, we propose to have what are called validators, which are essentially miners who would validate the transactions that are generated and log them into the respective local blockchains. And for querying the blockchain up here, we assume there's, say, a query manager, essentially a global validator. So, say a consumer wants to access the product story. The consumer could query the blockchain query manager, and this global validator will then have access to all the local blockchains, and this validator can then pull information from the respective blockchains to create that particular product story. So just to give you a simple example, right? Sort of, let's say you've bought a chocolate bar, and let's say you want to find the product chain for that chocolate bar. So this is showing you a range of transactions that map the chocolate bar back to where the cocoa was produced and, say, where the milk was produced, right? So you could actually generate something like this using our particular solution. Right. Okay, so lastly, I've just got a couple of minutes left, so I'll talk briefly about some of the open issues that we need to deal with as we move forward. So firstly, we have the issue of centralization of power. Now, this is showing you a picture from a few months back where even though Bitcoin is supposed to be completely distributed, right? We've seen that that's really not the case. There's a fairly sort of small set of miners who actually have a lot of power in the Bitcoin blockchain. So for example here, you'll notice that the miners which pool together under, say, bt.com have 30%, are mining 30% of the transactions in the Bitcoin blockchain, right? So this is sort of breaking away from the original argument that the blockchain should be distributed. This is actually showing us an instance where we are actually losing out on that distributed nature by having few entities having a major stake in the blockchain. Secondly, we have issues with a lot of vulnerabilities. Now, this, I must say, is not specific to the actual blockchain concept, but more to do with the ecosystem surrounding how blockchains are managed, right? So due to these, there have been instances where a lot of coin was actually stolen. So you see some of this information here. You've also had a lot of Trojan software been installed on people's wallets. So when they enter their wallet password, someone takes over their wallet and then steals all their money from their wallet. So again, this is not specific to blockchain per se, but more to do with the ecosystem. Thirdly, you have the issue of privacy, right? So some of you might be aware of the GDPR, the fact that the consumers should have the right to be forgotten. Essentially, all their information should potentially be erased if they really wanted it to be from the service providers. And given that blockchain is actually a immutable database, which means whatever information you store will remain there forever, right? So then we have a conflict. If we want people to be able to remove data, how do we do that? Because the blockchain doesn't allow for that. So we've actually done some work on this. I won't talk much about this, but in this work, we've come up with a mechanism where you could potentially remove certain information from the blockchain under certain circumstances, right? So if you're interested, certainly I can pass you on this particular paper. The next issue is the performance aspect, right? So, okay, people are proposing a lot of blockchains. How do we actually benchmark them? So there's this very interesting work I found recently, which has come up with a framework for analyzing private blockchain. So I think this is something that's quite important that the community must do as we move forward. And then the next issue is the trust of the information that's actually stored in the blockchain, right? So fine, once the information is in the blockchain, we can be assured that it stays there and no one would verify it. But the question is, how do we know that the information that's actually added is actually correct in the first place, right? So for example, down here, up here, sorry, let's say we have some information about, say, a product being organic that's being stored on the blockchain. But who's actually verifying that this is organic in the first place and logging that into the blockchain, right? So these are still open issues that need to be solved. Finally, you have the issue of privacy. Blockchain is an open database inherently, so everything is open. So then the question is, how do you sort of ensure some privacy given that all the information is open to the public? This really applies to public blockchains, by the way, not to private blockchains. And there is some work sort of looking at ideas like zero knowledge proofs and so on, which could potentially solve this problem. And then finally, you have this whole issue of ICOs, right? So this is showing you a timeline of how ICOs are being created, right? So we started in, if you go back, in the early 2017s, there were very few ICOs. And then in the later part of 2017, you see a lot of people coming up with ICOs, attracting funding, and so on and so forth. And the problem with this is you don't know which ICOs are actually trustworthy, right? A lot of them are failing for various reasons. Some because the technical idea was bad, some for other various reasons, and so on and so forth. So this is just something that we need to be careful, right? So for example, here it's saying about 46% ICOs have already failed, and that's quite a large number, say, compared to IPOs, right? Okay, so I think that concludes the talk. Just looking forward, I think blockchain inherently is a very interesting area. Particularly if you're, say, you're a new PhD student or a young academic. I think there are many interesting directions. Of course, there's a lot of hype, but if you take away some of that hype and you focus on some of the concrete problems, there's a lot of interesting things yet to be done. Stuff like how do you mathematically model the blockchains, the issues of scalability and performance, new applications, and perhaps some interaction of blockchains with machine learning. Could be of interest. So yeah, that's it.
Thanks very much,
Yeah,
Sayın.
thanks.
Çok teşekkür ederiz. Sorular için 5 dakikamız var. Dolayısıyla soru sormak isteyen varsa soruları açayım.
Hello, thank you for the wonderful presentation. I have a question about topology of the network. Let's say I have a factory and I have like 10,000 networks that are connected at nodes in the network. So should they be in the same cluster, or who is responsible for deciding the topology?
Okay, so yeah, good question. So you're asking how do we set up the topology, right? So yeah, this could be done in various ways. So for example, if you're talking of a campus like this, right, and you have 10,000 sensors installed on campus, you could kind of use the inherent geographical topology of the network to create these clusters. So you could say I have a cluster that covers this seminar room, another building, and so on and so forth. And essentially you could create this sort of nice hierarchy based on some of this physical information that you may have.
So is there like an ideal number a cluster should have? Like it shouldn't have like more than 100,000 nodes, but it should have like more than...
That's a good question that we've been asking, and frankly, I don't have an answer because we haven't been able to test it out on such a large network. As I said, we have an implementation under development, which is going to be ready soon, and we're going to at least try it out, say, in a 20, 30 node case to begin with. And then we'll try to scale it up, and some of these questions would be answered then.
Thank you.
Thanks. No.
Thank you for the wonderful talk. I have one question. Do we have any known attacks against blockchain or its implementations? You have mentioned about some incidents, but they don't seem to be directly against the implementation.
Yeah, that's again a good question. So the question was, do we know of any known attacks on blockchain? So certainly one very well-known attack is what's called the 51% attack, where if a malicious entity gets control of more than half, essentially more than the majority of the nodes in the blockchain, they could then potentially control everything that's being added into the blockchain, right? So that's certainly a very known attack. The way to get around, I think, some of the mechanisms that we have put in place where, for example, we require nodes to have a certified public-private key pair to be able to be part of the blockchain, perhaps could prevent these spam attacks spam accounts being generated, which may prevent someone from taking over the attack. And this, I must say, only applies to a public blockchain. Of course, in a private network, you would have more control.
Hi. First, I need some clarifications. In the first paper that you mentioned, for the spam detection, the PKI-based solution is only for the Genesis transaction, correct? Not for the all public keys of the entity. So, and you also changed that the public keys are changeable. So, is there such an effect that, and there is no other ID, correct?
No.
Other than the public key. Then, if the public key changes, does it have any effect in the trust calculations, because the ID will change all the time?
Yeah, that's a good point. So what we do is the way we have structured the transactions, we actually keep a link to the previous. So we create a chain across the.
Oh, so there is
keys.
actually the IDs are linkable, and
they are
the
in a way.
privacy issue here.
Yeah. I mean that's a trade-off essentially, which is very hard to solve, and we're still studying that.
Right.
Yeah.
Thank you.
Yeah. Thanks.
Teşekkür ederiz. Thanks very much.
Let's thank the speaker again.
Oh.
Just in recognition of your contributions to the conference, we have a small present for you, and this is for the PR for the university.
Yes, of course.
She asked us. So, over there, okay. So we'll take it.
No.
Okay.
Biz onun etrafına mı?
Small communication.
Okay, thank you.
Thanks a lot.
Yeah, thanks.
Thanks.
Thank you.
Şimdi o zaman saat 11'de sessionlarımız başlıyor. Kahve aramız var. Ya o takip ettiğiniz levhaları tersine takip edebilirsiniz ya da bahçenin ortasından geçebilirsiniz ama bahçede bir inşaat var, dikkatli olmanızı tavsiye ederim.
Konuşmacılarımız ve oturum başkanlığını bir 10 dakika önceden odalarda alabilirsek seviniriz. Teşekkürler.
Nasılsınız?